which is, so if I were just using, let's say, polar NRZ or BPSK or something, my nominal bandwidth, I've said we're going to use this expression. This actually depends on the particular modulation scheme. Normally we're proportional to 1 over TB, but to just give us a starting point, I've said we're going to assume that constant proportionality is always 2, which is not always true, but it gives us a place to start. The nominal bandwidth, 2 over TB, which would be 2 times 10 to the 4th power hertz, which is 20 kilohertz. Okay, so what I want, that is the required bandwidth. The spread bandwidth is 2LC over TB. So what I want to know is what's LC. So I know 2 over TB is 20 kilohertz. I know the available bandwidth is 1 megahertz. So what I want to know is what's LC. So 2 over TB, the nominal bandwidth, is 20 kilohertz. The true bandwidth, the all available bandwidth, is 1 megahertz. And I know that B is equal to 2 over TB times LC. So therefore LC is equal to B divided by 2 over TB, which is 1 megahertz divided by 20 kilohertz. I can write that as 1,000 kilohertz divided by 20 kilohertz, which is what? 50. So what I'd want is I'd want to select LC to be equal to 50. So again, that's what we mean by spread spectrum. We're spreading it out over all available bandwidth, but we're cleverly choosing these codes so that they don't interfere with each other very much. And it turns out that the larger LC is, the easier that task is. Okay. How do we get these chip sequences, or we also call these spreading codes? Actually, let me write that down. So we call chip sequences is the same thing as spreading codes. So you might hear both terms. So spreading codes, that just means a code to spread the bit over all available bandwidth. Okay. So how do we get these spreading codes? We talked about this a little bit last time. Let's do another example. They come from what's called maximum length shift register sequences. So a maximum length feedback shift registers produce spreading codes. In practice, it's a little more complicated, as I mentioned last time. What you do is you connect 2 feedback shift registers together to produce a gold code, but we're not going to take that extra step in class. We're just going to deal with maximum length feedback shift registers. So here's one. So here's my shift register and my connection. Here's my output, and my connection will be, I'm going to take the modulo 2 sum of those two. So let's call this flip-flop M for memory 0, M1, M2, M3. So how do we check to see if this is a maximum length feedback shift register? Well, for one thing, if it is a maximum length feedback shift register, what would the period be? So we said last time, okay, for one thing, remember that if I plug in 0 here, it always comes back to 0. So the period of that is 1, so that's obviously not allowed. How many possible states are there with 4 flip-flops? 2 to the 4, which is 16. So I exclude 1, so the maximum length is 2 to the 4 minus 1, which is 15. So it's maximum period is 2 to the 4 minus 1, which is 15. So basically what we have to do is we have to start with some non-zero state and show that the period it takes to get back to that state is 15. Because if that's true, then it must have gone through all of the non-zero states in order to get back to the original one. So let's start with this one. Reading from the left to the right. And here I want A, which I'm going to call this, the feed into the next state. And I can read the out directly from here because it's the same as the contents of this shift register. Okay, so what is A in this case? That plus that, which is 0. So I feed that back to the beginning. What's A? 0. So let's go through this. Now it is 1. Now it is 1. 0 plus 1 is 1. Now it is 0. Now it is 1. Oops. Now it is 1 plus 1 is 2, mod 2 is 0. Now it is 1. Now it is 1. Now it is 1. Now it is 1. 1 plus 1 is 2, mod 2 is 0. How am I doing here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, I'm going to continue over here. I have 0, 1, 1, 1. The A value is 0. So I have 0, 0, 1, 1. The output is the A value is 0, which gives me 0, 0, 0, 1. The A value is 1, and I end up with this. And the same as that. And that took me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Actually, I should have started here. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 is the period. So this is a maximum length shift register. Not all connections are maximum length shift registers. Actually, very few of them are. It's just that I'm showing you the examples that are. So basically the idea is maximum length sequences very nicely mimic random binary strings. We talked about some of the properties last time. But what we want is for we want a nice random looking string because we know interference, as we're going to show today, is caused by the cross correlation between sequences. We want to keep that cross correlation as low as possible, and random sequences or random looking sequences tend to have very low cross correlation.